name is Nur Alia Akila binti Asman. For the first theorem, we will prove that a subgroup of a cyclic group is cyclic. For the first step, we will let a group G with a binary operation S3 be a cyclic group. So G is generated by A, and we can write the entire group like this, where A power of n such that n is an element of integer. Now we are trying to prove that every subgroup of this group is cyclic. Let H be a subgroup of G, and we can just denote it as H is less than or equal to G. Our goal in this part is we need to show that H is a cyclic in two cases, which is trivial case and non-trivial case. For trivial case, subgroup H is an identity element. We know that the subgroup of an identity element is the trivial subgroups of G and always a subgroup for any group we have. So if H is our trivial subgroup, then the identity element is its own generator. So it is proven that H is a cyclic. Next, for non-trivial case, we assume that H is not trivial case. So in this case, we will have non-trivial element, and we call as non-trivial element X is an element in H and also in G. From this, we can tell that X is equal to A power of n for some n where it is an element of integer. We let m be the smallest positive integer such that A to the power of m is a subgroup of H. We let B equal to a power of m. So now we are going to claim that our subgroup H can actually be generated by this element A to the power of m, where it is equal to B. So it can be generated entirely by this element B. To prove our claim that H is cyclic, we need to show that any element in our subgroup H can be written as a power of our element B. Let's say C is any element in our subgroup H, and we can write C equal to the A power of X for some integer X. We will use the division algorithm to show that a subgroup H of a cyclic group G is a cyclic. So we are applying the division algorithm to this integer X and the integer m, which we said was the smallest positive integer, such that A to the m is in groups. So we can see that there exists unique integers Q and R, such that we can write X as m times Q plus a remainder R, where we have R is greater than or equal to 0 and less than m. So now we have X written like this. We can rewrite our element C as C equals A to the power of X, which we can write A to the m times Q plus R, and we can rewrite this where we have A to the m to the Q power times A to the power of R. We call that inverse A to the m to the negative of Q, and multiply this inverse to the both sides. We will get like this. The reason why we are doing this is to show that in fact A to the R is an element in H. Let R must equal to 0. So we can tell that A to the X is equal to the A to the m times Q. So we can write that as A to the X is equal to the m to the Q power, which equals B to the Q power. From this, we can see that H is generated by B, since we took any arbitrary element C in our group H and show that it had to be a power of B. So our proof is cyclic.
This is example of theorem 1. Find all the subgroups of integer modulo 18. Let group of integer modulo 18 under addition is cyclic. Then the subgroups of integer modulo 18 are also cyclic. We list the element of integer modulo 18. Then we find the divisors of 18. Divisors of 18 are 1, 2, 3, 6, 9, and 18. We will construct a table under addition for integer modulo 18. There are 6 subgroups that generate by 0, 1, 2, 3, 6, and 9. And notice that every subgroup there will be an identity element. Then we will identify the element of every subgroups that generate by 0, 1, 2, 3, 6, 9 by using addition table for integer modulo 18 that we was construct just now.
Hi, my name is Azian Nur Azian binti Azhar. Let G be a finite abelian group. Suppose that G is equal to n, k less than n. Let m element of n be a divisor of n. Then, n is equal to kp for some prime p and k element of n. By Cauchy's theorem, there exists a subgroup H less than or equal to G of order p. The quotient group is formed as G is abelian, so H is normal. Then, G over H less than n. Therefore, G over H satisfy the inductive hypothesis. Next, all divisors of G over H correspond to subgroup of G over H with appropriate order. K divides G over H. By inductive hypothesis and lattice isomorphism theorem, there is a subgroup H less than or equal to K less than or equal to G such that K over H is less than or equal to G over H and K over H has order K. Since H is finite, this implies that K is equal to KH equals to KP equals to M. Therefore, there is a subgroup of order M. Example of Theorem 2. G is a finite abelian group that has order 24, where G equals to Z24 equals to Z8 direct multiply Z3, or G equals to Z2 direct multiply Z4 direct multiply Z3, or G equals to Z2 direct multiply Z2 direct multiply Z2 direct multiply Z3. Next, Z8 has subgroup of 0, 2, 4, 6. Then, subgroup of order 12 is 0, 2, 4, 6 direct multiply Z3. 12 can divide 24.